Exam 1 will be 1 week from today. In class, no calculators, but you get 8.5 by 11 inch double-sided sheet. All this is in world class documented for you. And an integral table of your choosing. Get a good one. I gave you a good one, so make a copy of that, make whatever. You don't need the whole thing, just bits of it. And I think I'll probably even give you any weird formulas that I might ask you to use in a problem like this. We'll talk about that. So yeah, there's a review guide up, like exactly what's on it. There's also a web work assignment for review that is not required. That web work is not required, but highly recommended, right? And for the rest of this week, I'm not lecturing. So what I hope is that you'll come in here Wednesday and Friday and work and practice integrals getting ready for the exam. So there won't be anything new after today. I do have two new things. One new thing really to tell you today. It's not a technique. You were just responsible for substitution, integration by parts, partial fractions, and using a table. And again, we need to talk about this because this can get kind of fancy. And then hyperbolic functions, which is what I want to talk about today. Because people just don't know much about those. And it's a really good chance to exercise the power of knowing how to integrate, even though you don't necessarily understand what you're integrating. So that's why I like talking about these. Anything you all want to talk about? See, there's a web work right now. I can start off with that. Does anybody have any questions on that web work you want to address? Yes?
I think it was like number 7. I was kind of confused on.
Can you give me more
I think it was
deets there?
It's like x squared over x squared plus something.
yeah. X squared plus 36.
Oh, right. Okay, gotcha. Yeah, I totally know which one you're talking about. Okay, I'll pick a nice number. Something like that.
Mm-hmm.
Yeah. So, I've got a fraction. I've got a rational function, but the degree of the numerator's 2, the degree of the denominator's 2. I always want to get, anytime I have a rational function, I want to have that with lesser degree on top, strictly lesser. So the first thing I would do here is long division. So let's do that. So I can do a long division on this. I've got x squared plus, I'll put 0x plus 81. I don't think we're going to need that. And I want to divide that into x squared. So you literally just start trying to do it. And it goes in, let's see, x squared goes into x squared one time. I multiply this polynomial by x squared. You will have to do some long division on the final, or not the final, God. Not yet. Not yet. Subtract, you get minus 81, and so that's your remainder. X squared doesn't go into that. So this problem now becomes integral of 1 minus 81 over x squared plus 81 dx. So that's step 1, Gabe, and then this one's just going to go to x. So this is just literally, let me block this so Alan can see, unblock it. And this is like a arctangent form, kind of like 81, and this is a squared here. So if you look at the form du over u squared plus a squared, that's 1 over a arctan of u over a. So this thing here, I have a is 9, and this becomes 1/9 arctan of x over 9 plus c, and then that's, that simplifies to a 9 right there. But does that sound good?
Yeah.
That's the way to rock that one.
So that one's in the formula sheet, the du over.
Yes.
Okay. Cool.
Yes. It's a form that shows up a lot. This arctan thing seems to, I don't know, just seems to be around a lot. Anything else you want to talk about, friends? No. I think that site's not too bad, right? And if things are getting weird, it's just you need to slow down and check your setup. Okay.
I have one
Yes.
that was kind of tricky for me. No matter
Yeah.
what way I answered question 4, it just didn't want to take it.
Okay.
Not sure why.
I can come take a look if you think that's, or do you like? Is it kind of a general question you want to maybe talk about, Abraham?
Not sure. It was like
Yeah, what's the
x
problem?
cubed minus something.
Oh, let me take a look.
Yeah.
Let me take a look. So, x cubed minus, okay. So, let's take a look at that. We can talk about this together. So we've got like x cubed minus 1, and then a factored thing in the bottom. Sure, make it that. No, not that. Make it that. There we go. That'll be better. So the first thing I would do here is actually multiply out this denominator so that I could do the long division, right? Because I've got a degree 3 over a degree 2, so that tells me long division is what I need first. And I need to get a better pen out here. Please me. Oh, you're wonderful. Cool. So this bottom part is x squared minus x minus 6, and I'm going to divide that into this x cubed. Make sure to put double placeholders in there. So then, I always work with the leading term. X squared needs an x to get to x cubed. I multiply that times this. I get x cubed minus x squared minus 6x. Subtract down, and I get that. Those become positive, and then I bring down the minus 1. So let me stop for a second and see if this looks cool. Like if this is making sense, or God, maybe I did something wrong. Who knows? It happens pretty regularly. Is this, Abraham, is this sounding like kind of what you did? Yeah?
Yeah.
Okay, awesome. So we're all good on this? Because I got one more pass I need to do. X squared goes into x squared 1 time. So that's going to be x squared minus x minus 6. Subtract down, that becomes 7x plus 5. Yeah, this is a good one to do. So, there's a lot going on here. You got to do the long division, and then rewrite. I would suggest rewriting the problem. So this actually becomes integral of x plus 1 plus 2x plus 5 over, now we can go back to yield factored form, like so.
Now for this one, both of the ones on the bottom are additions. It's not an addition and a subtraction.
Oh yeah, I was just kind of mixing it up. It shouldn't matter too much, I don't think.
Just making sure.
Yeah, I was just trying to shake it up a little bit. And so then we have to do partial fractions on this thing. So I'm going to do the scratch work. So that's a over x plus 2, b over x minus 3. Flatten it out. That's the setup, and then flatten. Definitely we'll be doing this on the exam, promise. And I'll make it nice. Here we gotta like let x equal 3 to kill off that. So here we get 11 equals 5b. So b is 11/5. And then let x equal negative 2 to get 1. That worked out cool. Equals negative 5a. So a is negative 1/5. And then rewrite and rocket. So this should become integral of x plus 1 plus negative 1/5 over x plus 2 plus 11/5 over x minus 3x. And then just do the integrals. And hopefully you're seeing that these are log forms because they too, just like the arctan. Just looking good. Abraham, is that kind of like, so if there's some troubles, I'll have to come take a look.
I'll just try resolving it with all that
Okay.
stuff, see if it's still giving me issues.
That sounds good. You good? Nothing else?
I guess the one thing I would
Yes.
ask, because I haven't gotten to all of it yet, when you have an integral and you have like values for the integral that you have to plug in, do you just do it at the very end?
Yeah, let's say I had, that's a great question. Let's say I had this, like this.
You just like,
Then I would just, yeah, Sophie, I would just come down here and it ain't gonna be pretty, but yeah.
okay, cool.
All right. Cool. We'll be working on some stuff today, so I can come around and take a look at whatever you're working on. But one last new thing. I want to talk about hyperbolic functions because they're really cool in so many different ways, actually. No? No? Okay, I thought you were like, no. Yeah, I disagree. Strongly disagree. So, these are sometimes called the hyperbolic trigonometric functions. And I'll just define them first, then explain a little bit. So this is hyperbolic sine. And it is equal to 1/2 e to the x minus e to the negative x. That's one definition of it. It's actually defined in terms of an exponential function, which is pretty weird. If I were going to sketch out hyperbolic sine, let me show you how you could get a graph of it just by looking at this and knowing that here's e to the x, and that goes through 1. Here's e to the negative x, that also goes through 1. And when you're doing this kind of thing, you can do it visually. So notice here it's always e to the x minus e to the negative x. So it's this curve here, it's this heavy one, minus the other, and then take half of that. So right at x equals 0, it's 1 minus 1, I just get 0. They have the same value there, so when I subtract, I get 0. As I move out this way, this thing matters less and less. Can you see that? That if I take this e to the x, the height here minus this height down here matters less and less. It's asymptotic. So what you see is that this one always rides underneath that and kind of looks like a cubic when you come up this way. And then down here, when I'm taking e to the x minus e to the negative x, I actually get the reciprocal down like this, or the reciprocal process. So this is y equals hyperbolic sine of x. It looks like an x cubed. It's an odd function, if that is something that means anything to you. It's just, that's a comment about its symmetry. Let me show you the other one then. Hyperbolic cosine is 1/2 e to the x plus e to the negative x. So I'm basically going to take these two same graphs. So I'm going to take e to the x, and I'm going to take e to the negative x, and basically average them. So I can just do this visual average, and that's literally taking the heights and averaging the heights. So what you can see here is right at 0, where they're both 1, so when x equals 0, e to the x is 1, so this is 1 plus 1, 2 divided by 2, 1 is the value there. And then it's the average of these two things. So it's going to ride underneath here. This one is going to contribute less and less to the average. And it's going to ride up. And then over here, riding up like this. Since this one's lower, it pulls down the average just a little bit. And the way it pulls matters less and less the further out we go. So hyperbolic cos looks like that. Looks like a parabola, but it's not. It's actually a very interesting shape. It's called a catenary. It's not a parabola. This is the shape of the St. Louis Arch, upside down. So the St. Louis Arch is not a parabola, it's a catenary. It's literally a hyperbolic cosine curve. Hyperbolic cosine curves show up if you take a chain. If you have a chain that's got a bunch of links in it, you hold the ends at an equal height, the shape it forms is exactly a hyperbolic cosine curve. It's not a parabola. It's really interesting. If you can model, you can do a modeling of all this, and what you'll find out is it's this beautiful hyperbolic cosine. Why are they called hyperbolic? Well, let me explain. So, first day in class when I was talking about trig functions, I said something about knowing the cosine and sine graphs, and Sophie asked me, hey, I know the unit circle. Is that cool? And of course the answer was absolutely, that's cool. That's fantastic. So let's just talk about that really quick. What the hell is that? So here's the unit circle. How does this even relate to normal trig functions? Let's just quickly refresh how that works. So I come down here and I sweep out a distance along the circle. So notice this thing has radius 1, right? This is a circle of radius 1. So what is its circumference? What's the circumference of a circle of radius 1? This is just 2 pi, yeah. 2 pi, yeah, exactly. 2 pi r is your classic formula, and since r is 1 here, 2 pi times 1. So this is 2 pi units all the way around this circle. So that means that if I sweep out the measurement in radians, that's what radians are. They're really just the distance you're traveling around the unit circle. So like 2 pi radians means 360 degrees. Pi radians is just half this, that's 180. Pi over 2 gets you to 90. And then there's all the other options in between. So let's say I travel just pi over 4 units along that circle. We know that's 45 degrees, which is pi over 4 rads. And then from here, if I grab the x-coordinate, the x-coordinate's actually the cosine of this angle. And the y-coordinate is the sine of that angle. And so that's one way to think about what cosine and sine are. They're just these measurements of the horizontal distance and the vertical distance on the unit circle after you sweep out a certain angle. So that's the normal trig functions, and they use a circle. The hyperbolic trig functions, right, and this circle here is this one, x squared plus y squared equals 1. If I actually look at a hyperbola, boy, that is the shittiest x-axis. It just won't go. There we go. So I've got x and y. So if I've got y squared minus x squared equals 1, that is a hyperbola. You can think of it as a unit hyperbola. It's got asymptotes like this, y equals x, y equals negative x. It goes through the point 0, 1. Down here it goes through the point 0, negative 1. And then we also have this hyperbola too. There's one, and that's this one here. This here. So the hyperbolic trig functions are, assuming this is 0, if I travel a certain distance along here, that's the x. The x is how far I've traveled along here. The x and y coordinate of this is respectively the hyperbolic sine and the hyperbolic cosine. So this point right here, if I travel distance x along this curve, this is the hyperbolic cos of x and the hyperbolic sine of x. So there's like this parallel between the unit circle and the unit hyperbola. And doing things the same way is kind of why we get this, why we're calling this a sine and this a cosine, even though they have everything to do with E. Now at the end of the class, last month of the class, maybe a little more, 6 weeks, you're gonna see that there's an intimate relationship between E and the trig functions. Like under the covers in math, there's this deep relationship between E and sine and cosine. But we'll get there slowly. We got work to do before we get there. So let's take a look at another thing here. I can do derivatives and stuff with these things. So the derivative of hyperbolic sine, let's work that through. Well, we've got a formula, so it's the derivative of 1/2 e to the x minus e to the negative x. Take that derivative, you get 1/2 e to the x plus e to the negative x. Does this look familiar? What's this? That's the hyperbolic cos, right? So they have that property that they act like the regular trig functions with respect to differentiation. In fact, the derivative of hyperbolic cos is hyperbolic sine is hyperbolic cos. What's the derivative of hyperbolic cos? Can you do that real quick? Is it negative sine? Is it negative hyperbolic sine? Or is it something different? Because if that was regular cos, you'd know it, the answer is negative sine. How does this roll? You can just differentiate that formula there. Or this one here. We get So I think this picture, I gotta fix it. I think this is the one we used for hyperbolic, now that I'm thinking of. I think we just used that hyperbola there. Can somebody help me out here? What's the derivative of this thing?
1/2 e to the x minus e to the negative x.
Yeah, beautiful. So you get a minus out in front, and that is
Sine.
just plain old hyperbolic sine. So you're getting the swap between the two as you differentiate, but you don't get the sign change, the plus minus change. So it's actually easier. It's like kinder. It's a kinder trig function for us in terms of calculus. And we can write these relationships in a different way. I can say that the antiderivative of hyperbolic cos is hyperbolic sine, and hyperbolic sine's antiderivative is hyperbolic cos. So we have those relationships also. How do you think we could define a hyperbolic tangent? Just know what we have here. Any suggestions? Like
Hyperbolic sine over hyperbolic cosine.
beautiful, right? Like 'cause the normal tangent is sine over cosine. So we can define hyperbolic tangent to be hyperbolic sine over hyperbolic cosine. Yeah, beautiful point. Yeah, absolutely. What's the derivative of hyperbolic tangent? Can you do that for me really quick, please? You'll have to use a rule given a quotient. Some kind of rule that has something to do with quotients would be helpful here.
Hyperbolic cosine squared minus.
Yeah, let's go for it. You're gonna walk me through. I like it. So you're gonna do quotient rule, right?
Yeah.
So the derivative of the top is that times the bottom left alone. So this is where we're going to get hyperbolic cos squared minus
Hyperbolic sine squared.
hyperbolic sine. Yep. So top left alone times the derivative of the bottom.
Over hyperbolic cosine squared.
Beautiful. That's the quotient rule. So this turned into, I like the way you said it, hyperbolic cos squared minus hyperbolic sine squared, thank you, all over hyperbolic cos squared. Now, you know how sine squared plus cosine squared is 1? Hyperbolic cos squared minus hyperbolic sine squared is also 1. So you can literally take those formulas with the e's, simplify this out. This turns into 1 over hyperbolic cos squared. And what do you think a neat name for that would be? Like, so if I asked you, what's the derivative of tangent, what would you say?
Cotangent?
You would say secant squared, right? Secant squared. So what do you think we could call this?
Hyperbolic secant.
Hyperbolic secant squared. It's 1 over cosine, secant. So that's just sec squared x. So these patterns are really, really cool and fun. And it works just like everything you had with just a kind of a lot less hassle. We won't sketch out the rest. I think you should know what a hyperbolic cos and a hyperbolic sine looks like, but other than that, let's do some calculus now. So, you've got these basic rules. Let's get those basic rules back up. You don't need to rewrite these, I just had them up here. And then we'll do the tangent one also. Oh, this would be so what I would like you to do for me, if you could please, is just find this. What is the antiderivative of the hyperbolic sine of x cubed x squared dx? So you're going to need substitution. We're going to practice all our various skills today with this stuff. But the key is that once you understand how to do substitution, you just need formulas and you can integrate all sorts of things that you don't necessarily deeply understand.
I have a question.
Yeah.
For the third one, you did secant h squared, and then that becomes tan hyperbolic x, but on the other ones, you had it as hyperbolic u.
Oh, thank you. Yep, that's a good call, Sophie.
Oh, okay.
I meant to put you. Good call.
Cool, I didn't know if that was the first one.
Yes. Let me put up a couple here. Always a little trickier. I want a table, some sort of tabular thing. And then you're going to need a chain rule. Oh, actually, here. Yeah, you're going to need a rule like this. This is one of those special things. Like I've given you those guys before. It's kind of the more general version of it. That's just the chain rule, or excuse me, substitution put together. I would be X cubed, thank you. Yep. Being sloppy today. Luckily I got you here, so if you keep me driving between the lines. Is that one looking okay, the substitution one? And if not, let me know. I'm happy to talk about it. But I am gonna do this other one by table.
Just one question about that.
Yeah.
What happened to the x squared there?
So the x squared went away. So we're gonna let u be the x cubed, and then du is 3x dx.
Oh, the x squares cancel,
Yes,
right?
exactly. Yeah. Alright, so what do we got here? We're gonna do that. 3x I used, yeah. I hope you're kind of seeing this rhythm going on a lot, where you've got that kx in there, and you don't need to go through the whole substitution. You can just realize that a 1/k is coming out in front. And boy, it's sweet to not have those sign changes at all. That's really cool. So just rock that out. They say it's like almost automatic in some ways. And then put the table together properly. So we've got 1/3 x squared cosh, 3x, sometimes cosh and sinh. I don't know why we say sinh, but that's what we say. Minus 2/9 x sinh 3x plus 2/27 cosh 3x plus a c. We're good to go. Yes, Sophie.
What happens with the x? Just kidding, because it's the.
Is it all clear there, or do you need?
No, I understand now. I just
Okay.
trying to figure out what happened with the
Great,
x, so
great.
we're good.
Wonderful. Wonderful.
Where's the last one?
What, I'm sorry, what was that?
The last question.
That is a cosh of 3x, yes. Sloppy writing. Let me give you a couple more. Let's just practice doing all sorts of integration. All right, so how about let's do a series of them. So there's that one. And if you could do these, you're in really good shape. Why is this scroll? Let's knock these out. You already got it knocked out. I think it's preparing strategy. Have you seen Live at Pompeii?
No.
You need to watch that. It's like one of the greatest. Because I watched it again because we've been talking about it, and I was like, oh, it's so good. They like actually go to Pompeii and just play in this like ancient Greek arena. It's amazing.
Oh yeah, I'll be sure to watch that.
Yeah, you would love it.
I'm trying to see if I'm on the right track here, just this.
That's beautiful.
And this is canceling
Actually,
out
so
there.
actually, no, so we got a fraction.
there's no parentheses either, right? Or nothing acting like them. So I would let U be that denominator, thinking about log forms, du over u. That's what we're shooting for first, if we can get it.
You're actually going to make the same U substitution in both of them. It's just going to work out different. Well, that should be kosher too. I'm excited. What's the H? Don't forget to use the chain rule. The derivative of that inside part, that 2x, you're always going to get a 2 that comes on the outside. Check yourself up there, but then let's have a discussion about anything that's.
I got.
Yes, yes.
So why couldn't you pull the 1/7 to the outside of the integral?
So the 1/7 in where are we looking at?
On the first one side.
So the where I've got sine of 2x over 7.
Yeah.
Because that's so let's talk about that. You're all good, Harry. If I pull this 7 out like this, Gabe, first off, if it was 7 times this, I definitely would.
Oh. Okay.
But it's 7 plus that, and if I pull a 7 out in front and make this a 1, I still have to have a 1/7 in front of that.
Oh,
thing.
okay.
Does that make sense?
Mhm.
Yeah. So that was hopeful thinking, but hopefully you're understanding why I shouldn't do that. Okay,
Yeah.
awesome. I feel like, can we do this? Yeah? If you can do this, you are in really good shape. Alright, I got
So would it
one.
be for
Yes.
any case where it's just hyperbolic sine of something over cosine of, or hyperbolic cosine of the same thing square rooted? It would always just be the square root of the bottom?
Yeah, it would. I'd say that's a, yeah, because this, so if we have this, that, well, I don't know. It might not always be that nice because I think this 2 in here helped balance things out kind of nicely, because I think otherwise it would have been like a 1/2 square root of u like that. But I like looking for those kind of patterns and stuff. Probably better safe to say no, not in general. Other questions on this? Got one last thing I want to show you, and it has to do with using tables. All right, so let's say I've got an atrocious integral. Oh no, please don't do that. Okay, thank you. Thank you. So I'm looking at the integral table that I gave you, and I was given, let's say, this integral to do. So now there's a lot of ways to do that integral. But the easiest way is to look for a formula in the table. So if you go through the table, you will notice that on formula 67, I've got, so number 67 in the, assuming it's the table that I have. Oh wait, 68, thank you. Yeah, I was just realizing I had the wrong one there. 68, we've got integral cosine cubed of u du equals 1/2 2 plus, shit.
1/3 2 plus cosine squared u sine u plus c.
So what was in here?
It was 1/2 2 plus cosine squared u, and then close brackets sine u.
Like this? Yeah, cool, let's see, awesome. Cool, so that one I could just literally go to the formula. If this were a little bit more challenging, like maybe there was a 7x in here, I would first have to let u equal 7x, do the change, du is 7dx. So I would have to rewrite this whole thing in terms of u first, and what I'd find out is that I'd need a 1/7 out in front. So I'd carry that 1/7 all the way through. 21, thanks, yes. And then this u would be an x, and everything's all hunky-dory. Oh wait, 7x, wait, doop, sorry. And then come back and back substitute, so after I back substitute, then I would have my answer. Now I'm gonna push this up just a little bit. What if I had cosine to the 5th? That isn't explicitly in the table. So let's talk about how to deal with that. So let's say I've got integral cosine to the 5th of 7x dx.
It's
You
kinda
may or
in
may
there.
not have that. Oh, I'm sorry, somebody say
It's
something.
kind of in there. Under
Is it?
74, it's just to the nth power.
Yes, perfect. That's it. We're going to use that formula. So they have a much more general formula in there. Formula 74 says the following: integral of cosine to the n of u du. Now I've got to have to try to remember what that is. It is 1/n cosine to the n minus 1 of u. And then it's probably an integral, right?
It's sine of u. It's multiplied by sine of u and then added.
Oh wait, this has a times sine of u here?
Yeah, and then it's
Okay.
also plus n minus 1 over n.
Integral of something, right? Yes. Oh, cosine of n minus 2 du. Cool. Okay, so we have this general formula. We have to apply that here. Now this formula is what's called recursive, because it's going to help us understand a certain power in terms of a lesser power. So here I've got n equals 5. So using this formula, And you know, the higher up end is gonna be the more we're gonna have to unravel here. We get integral, let's write out the actual formula that we need first. So n is 5, so I've got 1/5 cos to the 4th u times sine of u plus 4/5 integral cosine of cubed, cosine to the cubed of u du. And we just did cosine to the cube, so we literally have to go grab that formula and plug it in here too. So this is 1/5 cos to the 4th u sine of u plus 4/5. Now go to that formula. And let's see, shit, I wish I hadn't, it's 1/3. Is this right? 1/3, 2 plus cosine squared of u. Somebody help me out with that.
And then sine u.
Sine of u. And all that plus c. And this is looking a little demented. So, cosine squared of u. Okay. So the key thing here is that I have to sometimes use multiple formulas in these recursive forms. If that had been cosine to the 7th, I would have first been taking it and described it in terms of a cosine to the 5th integral, and then I would have to take that cosine to the 5th and use this thing that we're doing here. So you can imagine this all just unfurling within itself. But for us, we're pretty much done now. We're just gonna let u equal 7x. So du is 7 dx, and you can see that a 1/7 comes out in front. So for us, our integral of cosine to the 5th 7x dx is going to be 1/7 times 1/5 cosine to the 4th of 7x times sine of 7x plus, oh gosh, let's, that's 4/15 times 2 plus cosine squared of 7x times sine of 7x. And then this is all still times the 1/7. I should have just brought that in, but I didn't. And really, I just want to make sure you understand what I'm doing there. And let me know if not. And do you see how this would work if we had cosine to the 7th? It would be a pain in the ass. You'd have to use this formula twice within itself. So yeah, if you're a computer science person, you do recursion all the time. Not used to doing it in math as much, especially in calc, but that's all this is. So, on the web work for prep for the exam, there's going to be some stuff you want to use the table on. And you'll get some practice doing that. So that's it, friends. That's all that's going to be on the exam. Everything I just talked about up until now. Let's just take the rest of the time to do what you see fit. If you want to keep working on the last web work, we can get that wrapped up. If you want to start on the, I think the new one is open. Maybe Voight can check for me. It's not open?
No,
Okay.
it opens at 1.
It opens at 1. Oh, that's weird. Let me fix that up. Is anybody going to start on that one now? Yeah, Voight. Okay, cool, awesome. So from here till Friday, we're just working on stuff, and I'm consulting with you. If you like make up a sheet of notes, and you want me to look over that for you, I'm happy to do that. Please check out the world-class announcement too, because there's actually some other problems that I put up there that aren't in web work, like written problems, and I've got the full solutions up for you. Alright, let's just make it right
check that out, Blaine. Let me know if that. Yep, cool.
Right there.
Another question.
Yes, let me, I've got it, hold on a second, yeah.
So maybe like last time, they're both the same. I don't know if I can just.
Oh, so for this one, this is when you have a repeated one, you have to have a fraction that has x plus 5 squared and then just x plus 5.
And then just X plus
Yeah,
five.
yeah.
Okay.
Does that make sense? Well,
Yeah, and then I'm trying to think how I would eliminate one of them to try and get
okay,
AOC.
so like let's do the setup first. So this is going to be,
So I think I did this stuff right.
okay, let's take a look while I'm here. Yeah, that all looks solid. Definitely. So you're going to have an a over x plus 5 plus a b over x plus 5 squared. And then that's going to equal this chunk here, so 75x plus, is that 249?
Yeah.
249 over x plus 5 quantity squared equals that. So then multiply through by that denominator. You're gonna get a times x plus 5
Equal plus
plus
B.
b plus just solid old b.
Oh, so then if we put -5, it cancels out, so you just get B. Okay.
Exactly. And then you'll have to pick another value to get the other one. but-
Okay.
Yes,
So I understand like how you did number 7 stuff, but then how I did it was,
Okay.
I just need to see why it doesn't work, but I pretty much
Okay.
let's go back here actually. So I actually made it like into a natural log, and then I substituted x squared plus
Yeah.
36.
It's unfortunately not a natural log.
Yeah.
That's the thing, because to have it be a natural log, you'd need a you need a 2x on top, or an x on top at least, because a natural log is du over u,
Yeah.
right? So it's not really a natural log, because there's no 2x to
Oh,
cancel.
Okay. That
If
makes
there
sense.
had been, or an x on top, that would have
Yeah.
worked out for you. So that's actually a natural, or an arctan form.
Yeah.
That's the only way to do that one.
Okay. Cool. That makes
Does that make sense?
And where's the like arctan form on the?
Oh gosh,
'Cause I think my
No.
problem is like I can't find these formulas fast enough.
well, there's no rush.
Yeah.
There's no, you got lots of time. Is this a touch screen?
Yeah.
Good. Well, let's see. I think they're down a little lower. Just kind of, let's see, so there's power. There we go. Here they are. Here's the arc function. So here we have inverse trig.
Mhm.
So there's the arctan. Oh wait, that's not quite, nope, I see, that's not quite the one we want. That's like literally if you have the integral of arctan.
Mhm.
So. Oh, here it is. So it's
Oh.
actually in these basic, it's in the basic form, so that's nice.
Okay.
Just right up there, does that make sense?
Yeah. So U will always be like U substitution, then A
Mhm.
would be like a variable like X or something.
Or the constant.
A constant.
It would be a
Okay.
constant. So like if this were x over 7 plus x squared, then a would be the square root of 7.
Okay.
So that constant, you're always going to take the square root of it.
Okay, that makes sense.
Yeah.
Cool. Thank you.
You're welcome.
So, I was having an issue with this guy.
Okay.
Not treating well here, alright. So I had it set up like this.
Yeah, that looks like a good setup.
Separate it into like this. Try to have x equals 5. think that this is right, but what you should notice here is they're asking you to let A be the one that's lesser. So I think if you put the negative 132/13ths there and the 108/13ths here, because I think that's it. Did you already try that?
I think I did. And I was trying, like if I messed up the signs or something, I switched them around and changed the signs.
Oh, okay. Okay, well that wasn't it. Okay, may I take a look here?
Absolutely.
Thank you so much. All right, so, double check everything. Yep. Okay, so that's perfect setup. Flattened it. X equal 5. What's 5 plus 7?
It's 12.
You got the hard parts down.
I was
It's just a subtle little. That could change a lot of it, though. I don't know. I'm gonna run to the restroom really fast. I'll be right back. That's a tabler for sure. Oh, it tells you that, I guess. Yeah.
So I would go look at the tables.
Yeah. So try that first, and then let's reconsult. Where were you trying? I'm just curious. Gosh.
Oh Lord.
Alex, yeah. I appreciate the gusto. Just giving it a shot.
This is just stupid algebra that I can't figure out, but I don't know how to find B and D.
So, okay, so you're probably gonna need. Let's see. Awesome. X equals 0. We got that. X equals 2.
Yeah, so you're gonna need, you can't yet, so that's good.
Okay.
That's good news, it's
Okay.
not you.
Alright.
You need one more equation then, Sophie. So like right now you know C equals 2, so you have this equation, negative, you have an equation in B and D.
Yeah.
2 equations in B and D. Oh, actually, no, maybe you don't need more. So you should just be able to, why do you not need more? That's the weird thing.
Well, because the problem is that B and D are both odd numbers, and so they won't like square to eliminate one of them. Because I could eliminate B.
Right.
I could use a negative number.
Yes, so I would put in like x equals 1 and get another equation, and then use that with one of these two to find our B and D.
Okay.
Does that make sense?
Yeah. Thank you.
Well,
It's a coming together one. Which one? Oh, okay. Yeah, I think there's actually an exact wording of it in U squared. There's, let's see, what was the problem? Can I see it real quick again? Cool, so we got U squared, okay. So. Okay, I think it's like if you squared plus. Bless you.
Thank you.
Wait, that's it? Oh shit. Yeah, it's not one of those. I think it's like more direct. Wait, here we go. There we go. There we go. Yeah. But there is a plus one in here, I think. So let's. There we go. Yeah, there you go. Yes.
I don't know if I could ask this, but how have
You
seen,
can ask whatever you want.
Okay, how have you seen people like make their note sheet, I guess? Did they like put all these on there?
No, don't put all this. No, don't put these integral tables. Don't keep this. Like I would like print out like a basic integral table,
Mhm.
and then like if there's any funny formulas, I'll give them to you.
Okay.
But like I would just have the basics. So like this page 6, like I would just have page 6 printed out,
Mhm.
and then anything else that's super funky, I'll give you.
Okay.
Does that sound okay?
Yeah, that sounds good.
Yeah, oh my God, please
Yeah, I
no.
was
Yeah,
about
like,
to, like,
I'm not a sadist. That would be really a sick thing to do, I think.
Yeah, I was about to print out like everything.
Oh God, no, please. I mean, you're welcome to print out the whole